This rifting and subduction, as it says here, have really shaped the Earth. In fact, we think that the Earth, 250 million years ago, not think, we know, we have evidence of that all the continents were actually a single continent, and it's even got a name. It's called Pangea. Um, and like, for example, there's a giant rift along the middle of the Atlantic Ocean, right? So and it goes right through. For example, it goes right through Iceland. Um, Iceland's a very volcanic region of the planet. Anywhere where you have subduction or rifting, you have mountain building and or volcanic activities. So you just think about the Rocky Mountains, right? The Rocky Mountains, the Andes, which is just really just a continuation of the Rocky Mountains. And then you go over, on the other side of the Pacific, you go down you know, the eastern side of Asia and China and then into Indonesia and Australia, even a little part, this side of the eastern side of Australia. It's volcanic, or it's a volcanic, and also they find themselves in with lots of earthquakes as well. I mean, just think about California. I mean, I used to live in Southern California. It was very common to have earthquakes, um, and you know, if as long as like things weren't falling off the walls, it was I mean, it didn't happen all the time, but it was very common to feel like a magnitude 4 or 5. It was not, it wasn't uncommon. Let's just say. So I lived there for about 9 years. I was in the Navy in San Diego, and then I went to college in San Diego, um, or my undergraduate in San Diego. All right. So anyhow, think about like Japan, right? The this the part of this this subduction and rifting, it goes right through Japan, and Japan is very much subjected to lots of earthquake activity. Uh, the Hawaiian Islands are another example of rifting, um, and you can actually follow the Hawaiian Island chain up towards the northwest, and the further you get along this northwest direction, there are even new um, islands forming in this Hawaiian chain. Uh, all right, so it's what's called plate tectonics. It wasn't always accepted for a long time. There was actually a guy. I think it was in 19. It says it right here, 1912. Yeah. So there was a guy that proposed this. I mean, and if you look in a really simplistic manner, you can kind of see the eastern coast of South America and the western coast of Africa um, look kind of like a jigsaw puzzle that they kind of um, looks like they would fit, and indeed that's exactly what the situation is they a long time ago, more than 200 million years ago, they were actually connected, and so we have really strong evidence of that. um, as time has gone on, and our ability, our technological ability has gotten better and better. For example, there are this, we can even measure the rate at which the continents are moving away from each other, right? That because of this mid-Atlantic rift. Um, and I mean, it's really slow. It's like less than 3 centimeters per century, right? So every 100 years, they're getting like 3 centuries, or they're getting 3 centimeters further apart. But over the course of millions of years, this has grown, and you have, this entire Atlantic Ocean um, you know, uh, between South America and Africa. All right, so that is as I said, this idea started forming around 1912. At first, it was complete. It was people just didn't believe it because I mean, back then the technology wasn't. We weren't really able to to prove this stuff. With experimentation. But that didn't prevent. I forget the guy's name. It was some guy. I forget what his name was. Anyhow, he proposed even back then this supercontinent called Pangea, which nowadays is completely accepted. Um, all right, so keep in mind this starts happening about 250 million years ago is when Pangea starts to break up. I mean, there's a whole it's exactly how that happened um, is actually been researched, um, in some detail. So this is and that's the another thing is there are here. Let's go back to this picture. Um, there are um, places in northern Canada that you find evidence um, of tropical life, of ancient tropical life, and so that means that this landmass at some point was somewhere near the equator, right? And so if you look at this, right, that this is showing you. So this is even before the Pangea starts breaking up. I mean, they had names for these things too. I don't remember them all exactly, but the Earth has gone through lots and lots of changes. I mean, so this is going less than a billion years ago, right? So you're talking about 650 million years ago. This is kind of the way the Earth looked, and then fast forward less than 100 million years, and it starts to look like this. It's still Pangea, and then about 250 million years ago, Pangea begins to break up. And so you can kind of start to see a little less than 100 million years ago, you start to see the what will eventually form the modern globe, right? The modern continents, right? You can kind of see you can see South America. You can clearly see Africa. There's North America. There's Europe and Asia, and then in modern times it looks like this, which tells you also that that's not going to be the case in the future, right? The because the Earth is an active world, that is, the interior of it is hot and it's still hot. That the surface of the Earth will continue to change, and that's exactly what's going to happen. Billions, well, at least a good billion years, maybe 2 or 3 billion years into the future. All right, let's talk about the Earth's magnetic field. I think I mentioned this before, but it is due to the liquid core of the Earth. The liquid core, of course, is made of iron and nickel, which are metals. Metals, electrons are free to move around in metals. That's why they make really good conductors. And so as the core spins, it spins at a different rate than the surface. And that causes what's called the dynamo effect. Now the Earth's magnetic field extends way out beyond the atmosphere. The atmosphere would be like this really close in, you know, uh, it goes up, maybe 100 miles or so. It's not exactly. It doesn't just suddenly stop. It kind of gradually gets less and less and less. But the Earth's magnetic field extends way out into space, And as I said before, that magnetic field protects us. So right now, the north pole of the Earth's magnetic field is actually um, it's actually it's in the South Pole, believe it or not. And so the only reason that a compass will point north is because this is actually this is the magnetic South Pole, right? And as I said before, that polarity has changed over geological time. Like I think it flips on average, right? It's not like some set thing, but on average it flips once every, I think it's 200, um, every 200,000 years, on average over geological time. Right. This is just imagining the polarity of a magnet. There's always a north pole and a south pole. I should mention that as well. With magnets, there's always a north and south pole. So north poles will only, so a compass anywhere on the Earth will always point north because this is actually the magnetic south pole. Right. And down here, of course, would be the magnetic north pole. And of course, it's the geological North Pole, right? That's what we call the North Pole. Um, but and compasses, for I guess the humans have had compasses around for perhaps 1,000 years. Nobody exactly knows. Um, there's some evidence that compasses probably started in Asia, but definitely don't know for sure. I mean, for example, we know that the Greeks knew about these special rocks that they called lodestones, which we know now are magnetic rocks. They contain a lot of iron in them, and they actually contain normal, just a normal magnetic field. Um, but what really changed for humanity is the point where we took one of these lodestones, these natural magnets, and you put it on something that floats, like a piece of wood or something like that, and you put it in like a little pool, a little container of water, maybe a bowl of water or something like that. And no matter what direction you turn the magnet, it always turns back the same way. And then humans realized, hey, one side always seems to point north, one side always seems to point south. And so we'll call that direction the North Pole and the South Pole. All right. So that's um, so as I said, it is generated by this thing called the magnetic dynamo effect. Excuse me, which really is just I guess it's every 250 million years. Sorry, 250,000 years is when the polarity switches. All right, and we have, like I said, we have actual evidence of this. If you look, on the ocean floors, where the lava solidified, the little magnetic rocks solidified in the direction of the magnetic field at the time. At the time when they solidify, when the lava turned solid. All right, and so we can actually map that out. The Van Allen belts are regions of heavy radiation. Actually, they were studied by a spacecraft called Explorer 1. That was the first spacecraft launched by the United States, and they were first proposed by this guy named Van Allen, and indeed they surround the Earth. And when astronauts pass through the Van Allen belts, they have to make sure that they're in their spacecraft and protected from the radiation. The radiation basically bounces back and forth in these Van Allen belts, and you don't want to be caught in. It would be like having 50,000 X-rays at once. if you ever went to the doctor and had an